You said something about volunteers, Trevor. I don't know. He asked me, would you like to volunteer?
Make sure it starts right.
Makes sense. I explained to him. I explained to him. It's obvious we've never had.
So you saw your schedule, so you're thinking on that.
You know, reach out.
Everybody says they like these animals. Back on that because his last year is 7 of them.
I just need to have but it works out.
Midland. That's the price.
For actually something nice out.
1 cent.
Yes, I have my.
You don't think?
I haven't been making these very often.
So you got cows and oil. We're gonna destroy the environment.
All righty, it is 7:30 and we are going to get started. You guys ready? All right, so normally I don't wear t-shirts to our meetings, but tonight is an exception. I found this t-shirt and it's got this astrophotography configuration that looks strangely like one of mine on it with wires going everywhere. And it says, yes, it's all necessary. So there it is. I love it. Yes, it's all necessary. What? Anyway, speaking of astrophotography, Stan contributed our beautiful image tonight for our opening slide. So Stan, would you like to tell us a little bit about it?
Well, it's M101 pinwheel in Ursa Major. I took it during full moon because that's when I was doing my slides for my presentation tonight, and decided to take pictures after the collimation to prove how well it works. And I was pretty proud of that. If I had a dark condition, it would probably be a lot brighter and more definite.
That is cool.
It's 21 million light years away. It's magnitude 784. I use an Optolong Pro light pollution filter, and had 5 hours. I threw away 1.2 hours of looks like clouds had come in, some thin clouds had come in and kind of dissipated the image. So I cut it back to 3.8 hours, and it did look a lot better. But as you can tell, there's a lot of little star clusters and clouds in the orange bands, and it's a lot of detail.
Yeah, it's really a good one, Stan. And this is like, what, 5-minute subs?
3 minutes.
3-minute subs. And this was done from Friendswood, right?
Yes.
That's impressive. That is very impressive. Can you tell me?
Of course, it's directly above.
Yeah.
In the evenings when I was taking that. Started that about 10:30. Just let it run all night. Till 4 or 5 in the morning, something like that.
Yeah, that is really excellent. Just super. So you sent me two, you sent me one, and you sent me a new one. What was the difference between the first one and the second
The new
one?
one was kind of washed out. I brightened this up a little bit to get some of the little stars and clusters and nebulas and stuff in the galaxy to pop out a little bit.
So it's just processing. So it's the same data, just processed differently.
So I didn't process that. I did it in Windows or the photo. It's just an app.
Okay.
You can make minor adjustments to images.
Yeah.
Like you take a picture of someone and you can do things with it
Great.
on Windows computer. And it's just got some little slider adjustments. I brightened it, and I increased the contrast a little bit.
That's great.
I didn't do that final process in serial.
Excellent. All right. Thank you, Stan. Hey, B or somebody, would somebody kill the lights up there? But do the all off button, please. I want to. Okay. Now you can see Stan's picture even better.
Oh, yeah, much better.
Yeah. Yeah. I've done M101 before, and that is a really excellent example of it. Okay, let's move on. Here's our agenda for this evening. And before we start, we always like to ask if there's anyone that this is your first time you've been here. I want you to hold up your hand, tell us your name, how you found out about the JSC Astronomical Society, and what your interest is in astronomy. Anybody first time here? Willing to admit you're the first time here? Okay, good enough. Oh, wait a minute, what am I doing? Yeah, there's that. Okay, so we have two email distributions, and one is for meetings only, and one's for everything. And B is holding up our clipboard right there. Isn't she a good door person? She's already got the clipboard up. She's holding up the clipboard. What you can do is you can tear off one of those tabs, and it has the two email addresses for you to send either for meetings only or for all the emails, general distribution, or you can take a screenshot of that. But if you send Ron or David an email, and they'll put you on our email distribution, you'll know what we're up to. A reminder to presenters, please use the mouse pointer that's built into this computer. All you do is you just move your finger around here on the mouse pad, and that moves this little red pointer. That's so the people online can actually see what you're pointing at. And the stream mic is in this laptop, and the auditorium mic is right here. So speakers, please don't wander around, because then people online can't hear what you're saying. All right. And please, no conversations in the auditorium during our presentations, because it's distracting to the viewers and rude to the presenters. So please don't do that. Okay, first up is Stan with SCT collimation using Batinoff and tri-Batinoff mass speed method. Stan Lamb.
Good evening. All right. Push the arrow button. Okay. He's already stole my thunder there. Okay, equipment. In this particular exercise and presentation, I used a Celestron C11 Edge HD SCT telescope with an equatorial mount and tripod with a one-shot color camera, ASI Air Plus controller, electronic focuser for hands-free fine focusing, iPhone, Batinoff mask, a tri-Batinoff mask, and what's highlighted or printed in red is the speed method item, is the light blocking mask, which was just cut out of poster board. And I got this idea from a guy on a YouTube video, Colorado astrophotography or something like that. You can look it up. I did a lot of research on YouTube and other places for SCT collimation, and this was the easiest, simplest, didn't require software or anything like that. It's just all pretty much visual. Okay, the procedure. First, what I didn't put in the presentation is that most people collimate their SCTs with the out of focus star with a donut pattern near the center of your field of view. And you just adjust your collimation screws until you get that donut in the center, and then you're good to go. But I've found that that's not quite enough. And I think there's software also that you can use to do that method, but I just don't think you get to the precision that is needed to get really good visual or
photography. So first thing is you allow your telescope to acclimate and stabilize in the environment that you're in. Once it's dark enough, I verified the telescope is focused. Even though it may be a little out of collimation, you still can get it fairly focused. Then perform a polar alignment, because while you're doing your collimation, you want to be able to track the star that you're trying to use, and you want to keep it centered. So you want to do a good polar alignment and activate your tracking. Then you select a star, go to or center a brighter star of high altitude to eliminate any atmospheric conditions that cause your images to fluctuate. In this example, this time of year, I use Regulus, which is almost straight overhead. And then use I did discuss it. Use the out of focus star method to verify approximate collimation. Okay, first step with the Bahtinov mask, in case anyone doesn't know, there's two types of Bahtinov masks. One is just the focusing Bahtinov mask, which has got 3 diffraction patterns, and it creates a pattern of 3 lines of the star, the image. And you install this over your corrector plate. The orientation doesn't matter. It can be rotated any angle. Take a short exposure. I was doing a half a second for Regulus for that particular telescope, and then I examined the diffraction spike pattern. And what you want to do is adjust your focus so that in that right image there, this one spike goes through the X pattern that is facilitated with the Bahtinov mask. And that, if you're out of focus, it'll be either to the left or the right of where the 2 X's or the 2 diffraction lines cross. And you can focus that until it gets in. So if you're doing this visually, those lines will be bouncing around because of the atmospheric stuff. But with the camera, I could take a short exposure and I get kind of an average. So I just take the average and get the average spike in the center of the other 2. Then I put the Bahtinov mask, the tri-Bahtinov mask on. But you have to line up some of the diffraction patterns or splines, whatever you want to call them, with the knobs. If you'll notice here, in the mask, there's a line that has this V, and you want to line that up with one of your collimation screws. And then when you do that, the other 2 will line up. You may have to adjust it slightly to get it, and it doesn't have to be perfect, just get it close. That will help you when you're actually, if you don't do that and you adjust screws, you'll be midway and it's just a nightmare. So you line it up like that. And basically you take a half second image, and then you'll have 3 diffraction patterns. It looks like 6, but there's 3 going through the center. And each one of those actually reflects how much out of collimation you are on a particular collimation screw. And you can adjust those. One way to do it is try to figure out which one's which. It's not real easy. And then adjust it a little bit, and then you'll forget which one I touched. And it's a mess. The speed method is to use this little light blocking mask, and you line it up. You have to cut it out a certain way so it matches the diffraction patterns, or blocks. It blocks 2 of the diffraction patterns and leaves 1 exposed. And the one you leave exposed here to the starlight is where the screw that you adjust. And that speeds up the process quite a bit for me and short-term memory problems. So you put your tri-Bahtinov mask on, put the light blocking mask on, and it will show, it's not a very good picture of it, but it'll show up just one of those 3 patterns. And the screw that you need to adjust, if that's not centered, is the screw that's exposed. So I call it uncovered, even though it's not uncovered. It's on the side where the diffraction patterns are uncovered. So you just do that, but as you make adjustments, you want to re-center the star. And with the ASR Plus, I've got a little bullseye there that helps to align the star in the center. So just keep making slight adjustments. It doesn't take much. And I get it roughly in the center of that one set of X crossing spikes and move on. Then I'll rotate the light covering mask, blocking mask to the next screw. And again, you line up this thing here and it'll line up all the way across with this screw and then that screw. And then this is the screw you'll adjust if necessary. And this one's, I took a little closer up view, but you can tell this one's a little bit out of adjustment. That is that one screw that's on the side of the uncovered diffraction patterns. So you can adjust that and you keep rotating around and around the telescope. You can go as many times as you want, because as you're adjusting one screw, you're changing the collimation for the other two. So I'll usually go around a couple of times and get it as perfect as I can. And when I'm done with that, I uncover the Tri-Botanoff mask and double check it. And usually I'm pretty close. And as you can see, these three, this line lines up right in the center. This line lines up in the center, and that one lines up in the center. And this only takes about 10 minutes once you get it down and you've used that light blocking mask. But also at this point, I usually take the Tri-Botanoff mask off and I'll put the Botanoff mask on again and refocus, and then I'll check it again. And that adds a little more time, but I've found that if you've done it just from a initial donut out of focus type method, that it takes a little while to get it perfect. And once it's perfect, at least in my case, because the telescope's basically set up all the time, we've got a 365 cover, and I cover up the legs and the whole telescope, and it's weatherproof and rodent proof. Hadn't had any rodents in there yet, no armadillos or raccoons, but I leave it up pretty long, and I'll check it every night that I use it, and it's been holding its collimation very, very well. But I do check it just in case before I waste 5 hours on photography. But that's about it. Some of the results. This is Polaris on the left corner there. It's double star, and then this is Corelli. It's a double star as well. They're fairly close together. And I had one of Mizar, and it turned out good too. But Mizar is like a triple star system, and I just didn't want to confuse anybody that the one I had taken a picture of was the immediate close pair. And then, of course, this was the Galaxy picture I took, and this is the kind of the faded out version. And then I, with Windows photo editing, I just brightened the image and add a little contrast to it, and it looked a little better to me. I was wondering how it was going to look on this big screen though, because it does have a little bit of a granulation. But I believe that's it. Yep.
So,
Any questions?
so Stan, I'm wondering about using the same method like on a Ritchie accretion. Did you see any mention of?
No, he only had, and I was only looking up SCT collimations, but
Yeah.
I was wondering to myself that if you've got 3 collimation screws,
Exactly.
it may work.
That's what I'm thinking, yeah.
It's worth a try, because I understand it's very difficult to
It is.
collimate those.
Where did you purchase the Tri-Botanoff mask? Where'd you get that?
They're sold at all these telescope
Okay.
places online,
Okay.
and you can download
Yeah.
3D printer
Okay.
programs as well.
Okay.
And I've got one for every SCT I've got. I've got a 14-inch, 11, and 2/8. So I've got collimation, Tri-Botanoff, and Botanoff, and the light blocking mask that I made myself out of poster board.
How would that work with one of those F2 versions?
Well, you don't collimate you take the collimation and the mirror out,
Yeah.
so you're not really.
So it's not going to be an issue.
Yeah.
That's not gonna work.
I think you're trusting that your telescope, your main telescope, is collimated already, and then you can collimate your camera. If you've got, you talking about like Star Zona has
Yeah,
that.
whatever the,
I think you can tilt it to collimate it.
and is there any way to automate your process?
What's that?
automate that process that you go through? Is there-
That was the automated process.
Well,
No, I mean, I'm just saying, would there, where it could do it, you put the thing on there and it mechanically moves it?
you could, but it's so much cheaper and simple to just cut it out of poster board and rotate it by hand and then check it. But I found that it works really good, and I think the proof's in the pudding. Yes.
How tight do you have to get? Because I noticed that you were a little off from center.
You talking about this image?
Yeah. How tight do you try to get it? I assume that was supposed to be right in the center.
Oh, you mean how close do I want to get the star in the center when I'm checking it? Well, that was close enough. I mean,
Okay.
it, even at slow motion, it would move completely on the other side of the center. When I have it zoomed in like that, it was just moving too far.
Oh, okay.
The little hand control for the telescope, it moves pretty quick.
Okay.
It's just a few arc seconds distance from the center. What you don't want to do is try to do it when the star is way over on the edge of your field of view. You're going to get all kinds of distortions doing it that way.
Oh, okay. Good.
Okay. Thank you.
Okie dokie. Paul Maley has a members minute, discovery of a parent satellite of minor planet 92590. Paul? Paul's not here. So he sent me this thing and he said, put your glasses on. He says, will you make a members minute out of this for me? And so Paul did something pretty cool. He said he's been trying to do this for many years. I think maybe since the 1970s. So let me read this to you. Paul Maley, who you guys know, International Occultation Timing Association and the NASA Johnson Space Center Astronomical Society, woo, yay, reports the discovery of an apparent satellite of minor planet 92590 based on occultation of the star UCA C4557-036088 on March 7th of this year. The magnitude of this minor planet was 19.66, which is 6.5 magnitudes fainter than the target star. Maley observed this from Carefree, Arizona, which is where Paul lives now, using a 28 centimeter telescope plus a Watek WAT 910HX video camera and OpenVTI GPS time inserter. The recording showed two consecutive occultations of durations of 0.55 and 0.64 seconds, separated by 0.46 seconds, corresponding to a chord length of 1.2 and 3.0 kilometers. The flux for the first occultation dropped to the limiting magnitude of the recording, approximately G, which I assume is green, equals 15.4, and R, which I assume is red, 14.8, and the flux for the second event dropped to that of comparison star UCA C4556-036487, Gaia magnitudes green of 14.1 and red of 13.7. The depths of these drops, 2.3 and 1.0 magnitudes in G and 2.3 and 1.2 in red, exclude a double star being the explanation for the light curve. And here's the light curve. The main body was modeled to fit the observed light curve using the larger diameter of 3.4 kilometers, with the fitted model having axes of 4.6 by 2.5 kilometers. The satellite was modeled as a spherical body with a diameter of 1.2 kilometers. The separation of this satellite was 0.0041 arc seconds and position angle 112 degrees, with a sky plane separation of 4.85 kilometers. Further, given the size ratio of these bodies derived from the occultation, the orbital separation is between 10 and 40 kilometers and possibly as large as 60 kilometers. And you can see more information about these at these two web pages below. But this is kind of a big deal. Paul's been trying to do this for a long time. This is a really great accomplishment that he was able to go out in his yard and actually make a measurement to show that this minor body, like an asteroid, had a satellite to it. So this is a really cool accomplishment for Paul. He's really proud of it. And I appreciate Paul sending this in for a members minute for us. So yay, Paul. All righty. Next up, we have Forrest with how do we model Earth's atmosphere in astronomers' perspective. Take it away, Forrest.
Okay. Thank you. All right. So can everybody hear me? Okay, so just the down key, enter key.
Yeah, enter key's fine.
Okay. Okay, so this is a little talk I put together just in the last couple of days. One of the things I did in my career was deal a lot with drag in the upper atmosphere. So I got to know a little bit about modeling Earth's atmosphere, and that's a big, huge scientific endeavor. But we kind of care about it a little bit as astronomers because we have to look through it. So I'm going to talk about that a little bit. But first, let's talk about the atmosphere. So it's a thin layer, and by thin, I mean thin relative to the size of the planet, not to the size of a human. It doesn't appear very thin to us. But if you're looking at it from, say, the moon, then it looks really thin. And it surrounds the Earth's surface, and it's retained only by gravity. The only thing that's keeping our atmosphere from flying away is gravity. And also it's protected from things like solar wind by the magnetic field. In fact, they think Mars used to have a significant atmosphere, and then when it lost its magnetic field about 2 billion years ago, it basically lost its atmosphere. That's why it's 1/100th of the pressure on Mars that it is here. So what does our atmosphere do for us? Well, it's a protective buffer between us and outer space. And so some of the things that it does is it shields us from some of these harmful radiations, particularly ultraviolet, but also X-rays and gamma rays. And it reduces the extreme diurnal temperature variation like you see on the moon, where the dark side and the light side of the moon, when the sun's shining on it, can change the temperature by hundreds of degrees. And it keeps us warm via the greenhouse effect. I've read something where the average Earth temperature is about 59 degrees Fahrenheit, averaged over latitudes, longitudes, time, seasons, all that stuff. They think it would be about 40 degrees cooler if it wasn't for the greenhouse effect. So basically it provides the chemical and climate conditions which allow life to exist and evolve on Earth. So it's a good thing. We like the atmosphere. A couple of interesting facts about it. It weighs 5 times 10 to the 18th kilograms. Now that's 5 quintillion. I had to look that up. 5 quintillion kilograms. And it becomes thinner with altitude. That's like a no-brainer. But the interesting thing is it just continues to keep on getting thinner and thinner and thinner. There's no definite boundary of the atmosphere with outer space. You can go up hundreds and thousands of kilometers and you still got a little bit of atmosphere up there. So it's mostly molecular nitrogen and molecular oxygen and argon down near the Earth's surface. And there's various amounts of water vapor, which varies quite a bit. That's what causes humidity. So it can be anywhere from a very dry environment like a desert, all the way down to like 10 parts per million, or it can be up as much as 5% in terms of a mole fraction. So the greenhouse gases, most people don't realize this, but water vapor is a significant greenhouse gas. And then the ones we always hear about, carbon dioxide and methane. And remember, the greenhouse effect is a good thing, but too much of a good thing is not a good thing, which is why we're worried about climate change. So up to about 100 kilometers, the atmosphere is well mixed because of turbulent mixing. So you don't get a lot of changes in the composition of the atmosphere as you go up to about 100 kilometers. But at about 100 kilometers, you start to go through this transition where that turbulent mixing no longer becomes the dominant driving physics on the atmosphere. You start to have diffusion, molecular diffusion. Also at about 100 kilometers, that's where the ozone layer exists. And the ozone layer basically captures all that ultraviolet radiation. And that's why we like the ozone layer. It keeps us from getting really, really bad sunburns. And but what that does is it causes photodissociation to occur.
So particularly the oxygen, the molecular oxygen in the environment dissociates into atomic oxygen. And then you've got this molecular diffusion. So as you go up above 100 kilometers, more and more of a light species start to propagate until you get up real high. All you've got is helium and atomic hydrogen. So, and this plot shows that. So this is a plot of the composition of the Earth's atmosphere. Basically, I think it's in volume fractions. So it's from an altitude of 0 to 1,000 kilometers. And you can see below that 100-kilometer boundary, it's just basically mostly molecular nitrogen, almost 80%, and then oxygen. And then what happens is that you start to get that photodissociation, and oxygen, atomic oxygen, really starts to climb. Such as if you're up at about the level of the space station, 300 kilometers-ish, 400 kilometers, the atmosphere up there is almost all atomic oxygen. And what that does is it makes things get very rough. Atomic oxygen is a very, it really has an effect on materials. So even though you think something might be smooth, it starts to get rough because of the presence of atomic oxygen. And then as you go on up, you see that first you start to get a lot of helium, and then it starts to fall off, and you're still seeing the hydrogen, the atomic hydrogen, climb up. So it's really not air anymore, what we call air up above 100 kilometers. It's something else. So as astronomers, why do we care? Well, okay, so it does all these great things, but from astronomers, as long as we keep our feet on the ground, so we're not like we were 2 months ago when, was it Jessica was here? Where she's launching balloons out of Palestine or anywhere else in the world to get her telescopes up high, or you're on Hubble or the James Webb. We got to look through that atmosphere. And one of the things that with that humidity that's a real bugaboo are clouds. Gosh, we hate them. As astronomers, just hate them, except when there's a drought. Then they're kind of useful. They make rain. But even in clear skies, our atmosphere filters much of the electromagnetic spectrum. So even though we need it to survive, when we're astronomers, this atmosphere can be a tad bit annoying. In fact, you heard that earlier when we were talking about to collimate the telescope. You want to look straight up so that you look through the thinnest amount of atmosphere possible instead of looking through the horizon when you got to look through a lot of the atmosphere. And like I said earlier, it removes a lot of the more harmful portions of the electromagnetic spectrum for us as humans, and but it leaves a lot of the visible light available. And then the other thing that it does, and this is a great thing to teach kids. I thought this to my daughter when she was little, and she astounded people. It also scatters light. In particular, it scatters through a process known as Rayleigh scattering. It scatters the shorter visible wavelengths, mainly like blue and violet, and that is why the sky is blue. So, there's a popular song about, questions that are mysterious. Why is the sky blue? Well, you can say, hey, it's Rayleigh scattering, and impress your friends. But so as an evidence of that scattering, the sun puts out about 1350 solar flux in watts per square meter at about Earth's distance from the sun. That changes a little bit because, of course, the Earth is closer to the sun in December than it is in July, so that's when it's up closer to 1400. But because of its filtering effect, on average, we only get about 1,000 watts per square meter. So from an astronomer's point of view, understanding the atmosphere helps us to plan how we can interpret starlight and sunlight when we're observing it from the ground. So here, picture says 1,000 words. So here's a spectrum. So we've got wavelength plotted on the bottom, and it goes from very short wavelengths and high energy per photon type of electromagnetic frequency all the way up to the the longer wavelengths, infrared. And if you kept going out to the right, you get up to the radio frequencies, and Doug knows all about that. So what the yellow is that's what the spectrum looks like at the top of the Earth's atmosphere. And then that black line is the theoretical Planck blackbody spectrum for a black body at 5250 degrees centigrade. You'll always see, like, when there's a color of light, like a TV screen or light bulbs or like, bright sunlight or whatever, sometimes you'll see a temperature associated with that. And it's like, that's not the temperature of the light bulb. What that is that's the temperature of the equivalent black body spectrum for that color of light. So the more softer lights, they'll have a temperature that's more like 3000 degrees centigrade as opposed to, bright 5000 degrees centigrade. And so then the red, that's the important thing. That's what we get down here on Earth. So first thing to note is way over here, these very short wavelength ultraviolets, they're all gone. They get filtered out by the ozone layer. And then you've got all these little absorption crevices that are caused by water. Water blocks quite a few things. In fact, we look for things. For intelligent life, and I never quite understood this, but there's these various places in the spectrum where we look because it's blocked out by the water. So we look for extraterrestrials in the water hole. It's got to do with the spectrum. I had that explained to me once, and I don't even remember why. But there's other absorption lines. There's O2, and so we have to kind of know this a little bit when we're planning to do things with like filters. As far as some things are already filtered. You don't need to filter them, and some of the things that they like do in terms of false color images, trying to figure out what to emphasize. So how do we understand all that? Well, one of the most important things in modeling the atmosphere is the temperature. It turns out that the most important variable in modeling the atmosphere is how the temperature varies with altitude. Well, we like things simple. So the simplest thing to do is say, hey, it's just a uniform temperature everywhere on the Earth all the way up, both sides of the planet, not day, night, everything. That's what we call an isothermal atmosphere. And so this is an idealized gravity-bound atmosphere model where temperature remains constant with increasing altitude. Okay, so in this altitude, you can actually take the differential equation that describes the density as a function of altitude and integrate it analytically. And you come up with this analytic solution that says pressure and density are exponential functions of the altitude. And there is a thing called the scale height. For Earth, it's 8.4 kilometers or 8,400 meters. And it's a function of the acceleration due to gravity and some other things. And so there's different scale heights for different planets. Mars has a different scale height than, say, Earth, and et cetera. But unfortunately, the temperature of the Earth's atmosphere varies in space and time. And so once we get away from that isothermal assumption, we have to boot in terms of doing the math on a sheet of paper and pick up a computer to do it. So we have to numerically integrate these equations from the ground up to the desired altitude to get things like the concentrations of different species, because these equations start to have things in there like diffusion terms, et cetera, et cetera. So here is what, for a simple model, here's what the temperature looks like as a function of altitude. So the plot starts at the Earth's surface at the bottom, and we've got the troposphere. That's the first layer of our atmosphere. And basically, it is the layer of the atmosphere where we start off at a nice balmy temperature on the Earth's surface that humans like, and then it falls to a very low temperature. Then we go through the tropopause, where we go up into the stratosphere, and the stratosphere is marked by starting at a very low temperature, and then as we increase in altitude, the temperature starts to climb. Then we go from there into the mesosphere, which is the medium sphere of the atmosphere, where once again the temperature starts to fall. And then we go into something called the thermosphere, which is starting right there at that point of about 80 kilometers, where diffusion starts to take over, and the temperature starts to climb. And it doesn't stop right there at whatever that is, minus 40 degrees Fahrenheit up at 100 kilometers. You keep going up 1,000 kilometers, it's a very high temperature. It's not a lot of energy, but it's very high temperature. And so that's why it's called the thermosphere. And then once it starts to get to like an asymptotic constant temperature, we call that the exosphere. And you might say, well, Forrest, where's the ionosphere? Well, the ionosphere is not really a layer of the atmosphere that corresponds to temperature. What it overlays kind of an upper mesosphere, of a lower thermosphere, and it's where that photodissociation is going on, because it also causes photoionization, and it makes us have an ionized layer of the atmosphere, which is great for reflecting radio waves. So that's why on the Earth we can pick up shortwave radio all around the planet, because the radio waves bounce off the ionosphere and kind of circle the planet. And so if we didn't have that, we would be restricted to line of sight communication via radio. So we wouldn't be able to do long distance radio transmission with shortwave radios. So people have taken those profiles and come up with these equations to model it, and then they plug that into the math. I'm not going to spend a lot of time on this. This is way too much math, so we're just going to skip right over that. So with all that, what are some of the models of Earth's atmosphere? Well, the simplest model are static models. Static models don't change with time, and they're the same everywhere on the Earth. The most used one is something we call the U.S. Standard Atmosphere. It first came out in 1962, and it assumes a non-changing variation. And so there's big books full of tables of values of like the density, all kinds of properties, pressure, temperature as a function of altitude. But it's just a function of altitude. Then there's some dynamic models where we start to account for things that change with time and space. The most important thing with the Earth's atmosphere for the upper reaches of the atmosphere, and I talked to this a little bit about this back in December, is our 11-year solar cycle from the sun. So our sun is a variable star, just slightly variable. It doesn't change a whole lot in terms of its solar output, but with the 11-year solar cycle, that upper portions of the shorter wavelengths varies quite a bit. So during solar max, you get quite a bit more ultraviolet and some of the upper energy or lower wavelength energies. And during solar minimum, those don't really happen as much. And what that does is it changes that exoatmospheric temperature that we assume from a relatively high value to a really, really high value. So it can go anywhere from like 600 Kelvin at solar minimum up to like 1600 Kelvin at a solar max. So basically the upper atmosphere is puffing in and out on this 11-year solar cycle. And that's something that's very important when we're planning ISS, reboosts and, how much fuel we're going to need. We need a lot more fuel to keep the ISS up at its desired altitude during solar max than we do during solar min. And so the U.S. standard atmosphere, basically, it just assumes that exoatmospheric temperature is constant, and it's 1,000 degrees. That's the assumption there. And then you've got even more complicated models that account for seasons, day-night cycles, and spatial variations like latitude and longitude. We as astronomers really typically don't go to that level of detail, but it is important for us at NASA when we're looking at things like high altitude aerodynamics for, say, like re-entry, because, if the atmosphere is changing a lot up there, we need to take that into account when we're planning the trajectories of like Artemis, the Orion coming back on an Artemis mission, or if we're taking a look at things like satellite drag, like trying to understand how much the station's going to come down in altitude over, say, the next 2 months because of drag with the Earth's atmosphere. So that's all I got. Any questions?
Yeah. So on the exosphere, the exosphere increases in temperature with altitude, is that correct?
The thermosphere.
No, well, I'm asking about the exosphere.
The exosphere, it's constant.
It's constant.
Basically, the exosphere is at this point where it's not exactly constant, but you're pretty much asymptoted to a value. So if I had that plot and it went higher than 100 kilometers, what you would see instead of a straight line, it would start to curve over and asymptotically approach some limiting value.
Okay,
And so that's what we call the exoatmospheric temperature.
that's my question.
Okay, so it asymptotes. So the shape of that curve, I didn't show it. It only went up to 100 kilometers, but as we start to get up above 400 or 500 kilometers, it starts to steepen up and then just become a straight vertical
Okay.
line.
That's my question.
Okay. Anything else? Okey doke.
Okay, now you can't say that we don't have variety around here, right? Yeah. All right, Rick, you want to say anything about sky and telescopes and DVDs?
We've got several DVDs, I think 3 of the DVDs up there as giveaways. Just go help yourself, and I think I got 4 or 5 of the Sky and Telescope magazines up there, so help yourself.
Thank you, Rick, for organizing that. Okay, so the meeting after the meeting, when we get done here, we'll get together at Mod Pizza. It's the one up in front of the HEB on Clear Lake City Boulevard. You just shoot up Middlebrook North, go west on Clear Lake City Boulevard past El Dorado, and in front of HEB, there's a nice little Mod Pizza there. We'll get together and talk about astronomy and other topics. Hope you can make it. Everyone's invited. Okay, we are going to take a short break, 10 minutes, and then we'll get back and have the second half of our meeting.
Groups go up there.
Yeah.
So, all the experts
In terms of magnitude, that's cool.
Good job.
Did you learn anything?
I did. The question that this guy asked,
Doug?
the one I'm kind of thinking of, he did much more informed manner. Hi, how you doing, Phil? Good. Is everything going? I met someone that knows. Yeah, because I said, because Lindy was gonna come, a friend of mine, Lindy, that's Pam, and Pam, you know, I was directly walk. Yeah. Yeah, downstairs. My friend Forrest. They said they lived together there.
That's the way I
Well,
Yeah, we'll talk about more.
The power.
They drive a, I love her car because I could cover a Tesla, how good someday. Yeah. Oh, okay, yeah.
Yeah, again, I just think that helps all the government. Yeah.
That's what her husband might have.
Honestly,
But she doesn't, because I think it's
She is in my window.
yes.
So they have a vending machine.
Yes. This one's close to the highway.
Okay.
And walking to the-
You want something?
Yeah.
Okay.
Well, I told the guy, I said, you need to show up a couple hours early. He said, well, you know, before you did it, or some people do it.
So what's going
Again, I'm architect, so you guys, we're all gonna meet up there.
Well, yeah, that was
Certain time.
but we had to consider those RVs, you know, we wanted to walk out.
Yeah.
It worked out.
Oh, it works out
Other
great.
than the streets.
Yeah.
I heard that gully, it spilled up water.
Yeah,
That was at least.
no, I mean, it worked out great usually.
Bring your stuff.
Yeah. And are you gonna do mostly visual?
Yeah. No, I don't have room. I'll bring my, I gotta play around and get it working. I did one time in my backyard. But yeah, well, I can.
Well,
It's been all these.
yeah, I got an AM5.
Oh, yeah. Yeah, I brought this to go through
I
it.
set it
I
up
went
in the
through
living
it.
room and downloaded the application.
I just tried to make it more.
I saw it online. You don't need to pay us on here and all the time.
Flashbacks about 3Ds. And then, right.
And then call
I
us.
had a problem shooting the game and not getting the nice. Which I should have known. I should have known without even, but I didn't. So there's
Sit on AM5. Something online where you don't need this.
How are you feeling?
Good.
Yeah. I'm thinner.
Hey, I'm thinner too, so.
Much weight did you lose?
Uh,
Well, you notice my double chin is practically gone.
yeah, yeah.
So I've lost several pounds.
I've lost 43 since. But I had, I wasn't doing what I did. But my chin, yeah.
Wow, eating soft foods really took away the double chin. I mean, it made me lose almost all attraction to sweetened sodas and almost all drugs.
Yeah.
I mean, I went to the top order grill. I had no desire for the barbecue, so I got like seafood platter with fish and shrimp, just no sauce and with green peas. I did splurge with I did splurge getting the blueberry pudding down.
Did Martin on Sunday?
Last thing I did, when I started, I just go to 24-hour fasting. So, 3 months.
Yeah. Yeah.
And I never had sugar, but carbs and processed foods gone.
Well, I teach most times.
I've been seeing all your acts going on Facebook.
haven't seen all your extra. Looks like you've done about 10 tournaments since the last time I saw you.
I just went to, I've gone to Waco, the big tournament. I got to do it quick. Because that was a real champion on tournament.
Yeah.
You get up against 256.
There you go. It's gonna be fun. So what's the next one?
Next one I'm going to is probably. I was getting trying to get one in Missouri. So my wife's gonna be out of town that weekend. So I go to
Where in Missouri?
that one. Or actually, I guess it's outside.
So,
there's one in Orlando.
what?
Too much to
Orlando?
because all my old schoolmates, so.
Oh, okay.
I didn't get too much trouble.
You don't want to do that.
And there's one that's gonna be on.
So you and Chris want to do
I think he's trying to put together all his little odd things to use with this. Maybe that false guy.
So is it you and him, or do you want to?
I think if I'm gonna do something, it'll be on my.
Oh, your own.
I just gotta figure out.
That's the hard part. Let me know if you want to do it.
I would love to, just, you know, I haven't done anything to speak about.
All right, let me get started here.
Okay, 10 minutes is up, and we're going to get started with the second half of our meeting. You guys are so, except for somebody. Same guy. No, you sit down, you be quiet. Almost. Yeah, Rick. No, I'm waiting you to be quiet so we can conduct the second half of our meeting. Oh, it just happens that Rick is our next speaker, though, so he'll get to come up here and talk anyway. Rick Slater with some interesting facts about the Pleiades. Now you can come down here and talk. Okay, so how do I work this thing?
Enter is go forward, backspace is go backwards.
Enter, go forward. Okay, all right. So this came from me trying to take a picture of what you see up there, and it's not something I shot. It's something I found, and so I went and shot the Pleiades, and my telescope almost framed it this way, but I should know better, but it didn't come out like that. And we'll talk about that at the end, and how when I go to the place we're going to in June, out in West Texas, hopefully I'll be able to get that one. And so I did a little investigating, which actually didn't take much time, because as I say, I should have known better, but I didn't. And I was also reading the Sky and Telescope for April issue, and they had a short article on some really interesting stuff about the Pleiades. So what I did was I went and did some research about the standard stuff, and I'll go through that, and then a little bit about what was in that article, which was, to me, fascinating. And then at the end, I'll show you the picture I came up with, and also show you why I quickly tried to put a graphic together to say why it failed. So Okay. First off, the Pleiades, also known as Seven Sisters, is a star cluster in the Taurus constellation of our Milky Way galaxy. In Greek mythology, Pleiades were the seven sisters of Atlantis, and I think it's Pleione. I'm not sure how to pronounce that. And they were transformed into stars. The cluster was also used by ancient civilizations for agricultural calendars because it was so easy to spot in the sky. Okay, so the Pleiades is approximately 100 million years old, started with about 3,000 stars when formed, and it was from a giant cloud of dust and gas. They're located about approximately 444 light years from Earth, and the brightest stars in the cluster have magnitudes of 1.6 to 2.9. It is part of the Taurus constellation and is also one of the nearest star clusters to Earth. The Pleiades cluster spans about 8 to 10 light years in diameter and currently consists of about 1,000 stars. And although only 6 to 7 are easily visible with the naked eye. So where did the 2,000 stars go? Over the last 100 million years, they have been drifting in the Milky Way, and now they're called the Pleiades complex. And if you can see from the picture, the Pleiades is actually that little kind of light reddish dot in the middle. The Pleiades complex is where it is spread out. And over the last 100 million years, they have been drifting in the Milky Way and, now called the Pleiades complex. They span about 2,000 light years. It's also a very young cluster. Astronomers believe that this is typical of star clusters, and after a few million years, most clusters vanish as they spread out in the Milky Way. This is just a quote. Open clusters like this are notorious for losing their stars. Astronomers estimate that the cluster will survive approximately 250 million years, after which it'll be lost due to really gravitational interactions. And so how did they figure this out? And this is the part of this short, really nice article that was in Sky and Telescope. So several researchers, and I won't name them here, they combined 3D motions of the Gaia mission. You can see the picture there of that, and stellar rotation rates from the transiting, it's called the TESS. I won't read that. And they did it for some 8 million stars. And apparently they folded in some data from ground-based telescopes. So what they did was they looked for stars that had similar rotation, similar chemical properties, and similar age to the Pleiades. And so if you look at both of these, this is what really fascinated me. And the pictures weren't in the article. I went and looked those up and put them in. But sometimes I'm just totally amazed at the science that goes on today. So what causes the blue color and makes it visible? And this was kind of interesting too. For one, the color emitted by the star. The Pleiades are primarily B-type stars, and I'll show you a little more on that later, known for their blue color. They emit radiation mainly in the ultraviolet and the blue light spectrum. Secondly, the nebula surrounding star clusters will reflect the color from the surrounding stars. And this is one thing they had in here, kind of interesting the way they put it, but like a flashlight beam shining off the wall of a cave, the star is reflecting light off of the surface of pitch black clouds or cold gas laced with dust. They call these reflection nebula.
However, the Pleiades Nebula is actually an independent cloud. And what it's doing is it's actually drifting through where these seven sisters are today. And they said they've got a relative speed of 6.8 miles per second. So, it's really interesting that it's drifted and it's right there now just for us. Little more, the B-type stars have surface temperatures ranging from 10,000 to 30,000 Kelvin. And actually it goes down to, I think, about 8,000 Kelvin. Their intense radiation contributes to the reflection nebula surrounding the cluster. They're actually, even though they're all blue giants, they're actually not that big because they're only about, in this case, 2 to 3 times the size of our sun. Also, they themselves, even though they look to us like they're fairly close to each other, they're actually kind of in a 3D. They're from 367 to 440 light years from Earth. So they're drifting in that direction too. Due to their intensity, they burn out quickly through their fuel in 10 to 100 million years because they're just so hot. They become supernovas, and then after that, becoming neutron stars, black holes, or white dwarfs. So, and this is just to give you an idea, the blue stars are sitting there in wavelengths that are into the ultraviolet or the blue spectrum. Our sun, the yellow star, is going to sit in there, and actually we see that as sort of daylight. 7,000 K is actually, for us and for photographers, would be daylight. And of course, then you've got your red stars that are sitting there, and they're only about 300 K or 3,000 K, excuse me. So where are we from there? This is the picture when I put it through my computer, and I had I only now in Houston use my hydrogen, oxygen, sulfur filters. And so I put it together as a nice color picture, and I expected to get something a little bit different than this. But if you notice, red is actually the hydrogen filter. It's the color that the computer gives you for hydrogen. And it's nice to know that all these stars are basically hydrogen. So that's what I started with. And then I kind of put this together so I could demonstrate it. When you look at the narrowband filters that I'm using, the oxygen falls really mainly in the greenish, light greenish maybe. Your hydrogen is sitting there in red, and so is your sulfur. So there's no blue. And of course, the blue stars are emitting in this part of the spectrum that's really blue and ultraviolet. So there was no chance of me getting any color. So when I go out to West Texas here next month, there we go. These are actually the parts of the spectrum that my red, green, and blue filters provide. So I should be able to get the blue spectrum if I do everything right. And in conclusion, the Pleiades are an interesting star cluster. And I have to say, one of the things that I've really enjoyed, and I tend not to read the big, long articles in Sky and Telescope all the time. I kind of read the shorter ones. And this one just appealed to me. And they've got a lot that are just like that. So I thought it was pretty interesting. And hopefully I'll be able to come back with a picture that looks like the one you're looking at now. Any questions? Question.
So from your talk, all these stars in the Pleiades are going to supernova sometime relatively soon, like in the next 10 to 100 million years?
That's what they say. But you know, the count. Well, go ahead.
Close for a supernova? Wouldn't that be a bad thing for a supernova like 400 light years away?
Possibly. I honestly haven't researched any of that. So, and the other problem was
a supernova that close to you. That's kind of, you know, pay up your life insurance.
well, The other thing, and I found this by doing a little more research on it, there was another group of astronomers that had done something, and they believed that nothing was really going to happen to them for about another 250 million years. So I'd like to side with them rather than where we are now.
I feel better now.
In fact, I was showing this to a friend of mine, and he said, "Aren't those two aren't those kind of counter to each other?" And I said, "Yes, they are, but they're astronomers, so you've got one's on this side and one's on that side." So, but that's what they had. Anything else? No? Okay. Thank you.
Oh, Rick, you had one more slide. Okay, so Trevor, I have a question for you. I should have asked you earlier. Sound that plays through this, it will go out through the in the auditorium? Huh?
But it should.
Okay, all right, thank you. All right, masers in space. So you guys, I haven't given you a talk about radio astronomy for a while, and I know you've been really disappointed. So here it is, masers in space. What is a maser? I see some people look at their watch all of a sudden. All right, masers. A maser is a microwave amplification by stimulated emission of radiation. So it's kind of like a laser, which is a light amplification by stimulated emission of radiation, but with microwaves. So a maser is like a microwave laser. And that's Calvin with his death ray. You guys ever watched Calvin and Hobbes? Okay, so maser emissions, they can occur from molecular clouds. They can come from comets. They can come from the atmospheres of stars or atmospheres of planets. They can actually just occur out in interstellar space. And how they occur is you have some atoms out in space, and there will be some kind of thing that we'll call a pump, which is radiation, which will pump those atoms into an excited state. And so then you have what we call population inversion, when you have a whole bunch of atoms that are all in excited states. Then when a photon comes along of the correct wavelength, that photon will cause that atom to release another photon, which just happens to be coherent to the first photon. That word I couldn't remember at Mod Pizza last time, Jerry, coherent. And the coherent means the photons have similar direction, amplitude, and phase. And then when this happens to another atom and another atom and another atom, pretty soon we got a whole bunch of photons. They're all coherent and they're all coming at us. And that's what a maser is. So just think about it a little bit. While we're all sitting here just minding our own business, we're all getting radiated by microwave lasers from space. It's true. One more thing to worry about. Yeah. How can we, all of us in this room, how can we detect masers? Well, what, are you guys laughing at my radio telescope? Come on. All right, how can we detect masers? Okay, it just happens that there's a methanol maser around 12 gigahertz. And it just so happens that satellite TV antennas operate around 12 gigahertz. How do you like that? Woohoo! So maybe we can use a satellite TV antenna to detect a maser. Now, what are the challenges going to be of observing a 12 gigahertz methanol maser with a satellite TV antenna? Anybody want to say it? What's going to be the challenges of detecting masers with satellite dish antenna? Satellites, exactly. Yeah, so we're going to be seeing satellites all over the place. They're going to be everywhere. So here's a plot from March 27th. And here I was out there trying to detect masers. And what happens is when this is over time, and these low samples down here are possibilities they may be able to detect a maser. But these ones that are up high here, those are satellites. Okay, there's satellites just everywhere. Okay, they're just all over the place. And so most of your samples when you do this are going to be duds. In fact, I've gone out some nights, I've only been able to get one good sample the entire night. The rest of them are full of satellites. Okay? So that's the challenge with doing this. Okay, so masers are pretty faint, so we need to figure out how can we increase the sensitivity of our radio telescope in order to detect these masers. And this is the sensitivity formula. And I've shown you guys this equation before, and I thought it was very nice of all you to not point out that there was an error in this equation when I showed it to you before. And I thank all of you for not embarrassing me to say that equation is wrong, because it was wrong. What I told you before was wrong. But this has been corrected, and this is the new and improved sensitivity formula. Okay, so over here on the left-hand side, we got F min, which is flux minimum. That's the minimum flux density that we can detect. And then here's a whole bunch of other stuff over here that factors into the minimum thing we can detect. And one of those things over here is the square root of NT, which is integration time or exposure time. So just like when we're doing astrophotography, we go out, the longer we expose, the more faint we can see, right? The longer exposure we get, we can see more faint objects. Same thing with the radio telescope. The longer I can integrate on this thing, the more faint I'm going to be able to see. Okay, so how can we increase our integration time? That's what we want to do. So the radio telescope I've shown you guys the most in the past is this one. It's 2.1 meter radio telescope, and it only points at one spot in the sky. So it's pointing at one spot in the sky. It's got a beam pattern that looks something like this. And when your celestial object goes by, then it detects it when it's within its beam pattern. So if you're lucky, you might get like 20 minutes or so of integration time per day with this scheme. And the truth is, it only is at its peak right at this very top. So only for a short period of time is it really at its peak sensitivity. So we're not getting a lot of integration time using this method. Is there a way to get our radio telescope? Yes, Trevor.
Farming.
Farming?
Lots of them.
Oh, when I get my farm, I'll do that. Okay, great idea, Trevor. Okay, is there a way in my backyard to get our radio telescope to track the sky and our celestial objects, thus increase our integration time? Is there a way to do this? Yep. We can mount a radio telescope to a German equatorial mount. What is that sound? Does anybody know what that sound is? What? Or? Good guess. What? Could be. Okay. Look at that go. And that's the most exciting thing you guys have ever seen? Yeah. What is that sound? Huh? Yeah? Anybody else? That is the power of celestron. You guys don't know that? That's the power of celestron. Okay, anyway, yes, that's the power of celestron you just heard right there. And there's our radio telescope mounted on a German equatorial mount in order to be able to track the sky and get more integration time. Woo-hoo. Okay.
That was from 3 different angles.
That was from 3 different configurations because I keep screwing up my configuration. I have to keep redoing them. But then when I had 3 of them, I thought, hey, it'd be kind of neat to run them all at the same time and make a big noise. And we could talk about how well, okay, Forrest, I got to tell you this. So a lot of you guys know Becky Ramatowski, which we all love very much, right? So Becky, we're at Fort McCabe one time, and I'm using my mount, which sounds like a broken coffee grinder. That's what that Celestron ASGT sounds like. And so she says, what in the, is wrong with your telescope mount? So it is the loudest mount you ever heard in your life. But anyway, it's loud, but it works. So, okay. We need to, how can we increase our sensitivity too? Another thing we can do to increase our sensitivity is we could actually get a bigger dish, right? Increase the area of it. It'll collect more energy, right? And it'll be able to receive fainter and fainter objects. Okay, so our previous radio telescope that you guys were laughing at a minute ago, my little 0.5 meter dish 500 over there, which I was showing you before. Okay, so I went out and I got a bigger one. This one on the right is new to me. It's a 1.1 meter. So it's about twice as big as the one I've shown you before, right? So since it's twice as big in diameter, that means it's going to be 4 times as big in aperture or area. So I should be able to get 4 times the amount of signal that I was able to get with the smaller dish antenna, right? By the way, this is kind of interesting. I got this on Facebook Marketplace. There was this Mexican family that had moved here from Mexico, but what they were doing is they were trying to watch Mexican TV stations in their from in their backyard. They had this dish. And somehow this Mexican satellite company sold them this thing, and they'd been using it for years and years and years. Now they didn't want it anymore. They put it on Facebook Marketplace for $100. I got it. So there you go. I've been looking for this for a long time. I finally found one.
And you can watch Mexican TV.
I haven't done that, but it's a lot bigger and it's heavy too, by the way. Okay. So did we gain anything by doing that? Here's our 0.5 meter dish, 500 dish, the smaller one. Here's the bigger one. And here's a couple sun crossings. So we'll go out and see, did we gain anything in sensitivity? So when I've done this in the past, I got 2.4 dB for the smaller dish. I got 9.19 dB with the bigger dish. That's pretty good improvement. And Forrest taught us all about solar flux unit here, which I didn't know about, but Forrest taught me about this. And the solar flux units on these 2 days is roughly pretty close to each other. In fact, it gives the advantage to this one here because it's actually a little higher solar flux unit on that day than it was here. But the satisfying thing about this is 4 times bigger. You radio guys, Lance, if I have something 4 times, how many dB should that be? Twice as big as how many dB?
3 dB.
3 dB. So 4 times as big is 6 dB, right? 6 dB. And look at this. Pretty close. So it's actually pretty close to the theoretical, what it should be, about 6 dB better. Yeah. So it makes me feel slightly like I actually might be beginning to learn something and understand what I'm doing a little bit. So I actually got, right around what it was supposed to be. So I was happy about that. And then here's the moon. Okay, so I've shown you the moon in the past with the 0.5 meter dish antenna. And that one got 0.063 dB, much lower, of course. And then with the larger one, I got 0.48 dB. So I did get, an increase in sensitivity with this dish. So we all believe that, right? Now, what are some bright 12 gigahertz masers, methanol masers? Here's 5 of them that came from this paper that's referenced down here. They go all the way from about 800 Janskys, Jansky being the unit of flux density used in radio astronomy, 800 Janskys down to about 150 Janskys. These W ones come from the Westerhout catalog. Westerhout is a catalog of radio sources. And NGCs, we all know NGCs, new general catalog. Cepheus A is actually just an active area in Cepheus. Then a lot of the masers that you find are actually referenced with a G in front of them. These are galactic coordinates. So they're actually just referenced by their galactic coordinates. So when you look at one like this first number after the G is the galactic longitude, which is the angle along the axis of the galactic plane. And then this is galactic latitude, which is 90 degrees from the galactic plane. So that's galactic latitude. But a lot of the masers you'll see will actually be in galactic coordinates. So these are 5 that, if you're lucky, you might be able to do these as an amateur. And there's this web page called the maserdatabase.net, maserdb.net. And you can go there and you can put in a maser that you're interested in, and you can pick a molecule that you're interested in, and it'll give you all kinds of information. Or you can also go there and just do a search on all masers and try to find out which ones are the most powerful, or which ones actually are going to emit the different frequencies that you're interested in. So that's a very useful maserdb.net. All right. Have we had any success so far? What do you think?
Yes.
Think I'd be standing up here saying, oh, sorry. Yeah. Okay. The truth is maybe. The reason is I've been trying to do this now for a couple months, and the facts are there's a lot of satellites up there. It's really tough to get any samples at all. So after several days, like 3 days of this, I was able to get 15 samples that had something, and that winds up being 1 hour and 15 minutes. And this is my signal. It's not very big, But the reason I think it maybe might be the right one, this is for G188, the maser I just showed you on the previous page. The reason I think it's maybe right is because the frequency is about correct. Okay, I expected this frequency, I got this frequency, it's off by this much. And you say, well, why is it off by that much? The oscillator that's inside this device is actually only has an accuracy of plus or minus 300 kilohertz. So it's within the accuracy of my oscillator. So it could be, and it's the only thing that's poking up here. So I'm hoping, and actually I should say it's also the right shape for what this one's supposed to look like. So given all that, I'm thinking that maybe this is a detection, but we will keep trying and we'll come back later with more results later. If you'd like to see this and more of my adventures, go to my webpage, www.holland-observatory.net, and that's it. Any questions? Right.
Okay, so you've got all these satellites up there, and you've got satellite signatures basically being generated.
Yep.
Is there a way to somehow isolate those and eliminate those? Or the software doesn't do that?
Well, it's pretty broadband because see what's going on is I'm looking at this one little frequency. I'm trying to get this one frequency, right? But Rick, what happens is when a satellite comes by, it raises everything up. All frequencies within my band go way up, and then they all come way down. So what I'm doing is I'm getting like this out of band stuff. They may be, an adjacent frequency, but they're so much more powerful than the maser. I mean, it's not like there's individual frequencies of trouble. It's raising the entire spectrum up and down when these satellites go by. They turn from, yeah, they're huge.
Now, the satellites are going to have data on them.
Yeah.
Right? So, like QPSK
Yeah.
data, have you ever thought about decommutating the data and separating it out that way?
Lance, I don't like satellites. I don't want to mess. Yeah, you could do that. You could use a satellite TV. You could use a satellite dish actually for detecting satellites. You could do that. But I don't want to do that. I'm trying to use it as a radio telescope.
What I mean is to tell the difference between a satellite and the masers.
Oh, well, the problem is that the satellites are so broadband. They're so broadband and they're so powerful that they just wipe out any signal. Yeah, they're huge. Yeah, you could never get the tiny little maser out of this gigantic thing. Yes, sir.
Have you come across any literature or information on the risks, like if you're working around radiation, sources like XRF or XRD, they make you wear like a little badge or whatever to collect it throughout your.
Oh, you're worried about me getting radiated by masers?
With the when you have the telescopes, you put like filters on there to make sure that you don't damage the optics and such, right?
Yeah.
Is there any concern about the lasers possibly affecting your equipment, causing any damage or any
No.
high influence of radiation?
No, the masers are tiny. I'd love to be able to detect them. Yeah. I'm not worried about that. I mean, let me tell you, when we go outside, we're getting radiated by a lot worse stuff than masers. I just try to, because Calvin with his death ray, I just kind of trying to be dramatic with that. But the masers are tiny compared to everything else. Don't worry about the satellites are way bigger than the masers are. Yeah. Any other? Yes, Forrest.
So if satellites are such a problem, I mean, is it just for this type of radio astronomy, or is it just all radio astronomy satellites?
It's when somebody's using a satellite TV dish antenna in their backyard trying to detect a maser. That's what it is. Because see, so Forrest, when I do the other radio telescope and I look at the neutral hydrogen, no problem. I never see a satellite ever, no problem ever. Okay. I see now interesting.
Maser detection.
It's just the maser thing because I'm using a satellite TV antenna in the same frequency range as the satellites. That's why I'm having problems. But yes, on the for neutral hydrogen, it's not a problem at all.
Now, this is a little bit of the next crazy question, but would this work a lot better if you were on the moon?
Yes, I'm going.
Okay.
Yeah, it would. But Forrest, actually, something maybe you can help me with this sometime. Okay, with the neutral hydrogen, what happens is even though I don't, I'm always getting a signal with neutral hydrogen. It's really fine. There's no pro with satellites or anything like that. But I get a lot of, like at nighttime, the whole base of the whole thing goes down, and at daytime, the whole noise floor goes down, and at nighttime it always goes way up, and in the daytime it goes down. It just goes up and down every day, and it must have some kind of atmospheric effect that I'm not understanding, but it's really consistent about how it goes up and down every day. And a lot of people think it's temperature, but I don't think it's temperature. I think it's something else.
Okay.
And if you ever have any ideas, let me know.
All right.
Yeah. You're kind of an expert on that, and that would be useful to know that. Anybody else have a comment, question? All right, good. Mazers, you heard it here first. Okay, David Haviland, Star Party News.
He's not down here yet.
I was sitting there wondering if I put my coffee into the microwave to warm it up, am I mazoring my coffee?
You are.
All right. Enter, right? There we go. Past events. I want to talk about most of these. March trip to the fort that got morphed into the multi-club Messier Marathon. That turned out to be a very successful event. We had an event of March 28th at the winery. April with the club shot to Fort McCavitt. And then April 25th, we had another trip to another event at the winery. All right, May 10th through 17th, Texas Star Party. I don't know if anybody's going. Not? It's okay. May 23rd is going to be a hack event. And then we've got a series of hack events down here. And then September 19th, the A-Day 2026 at Insperity. Aaron's picking that up and running that all right. El Dorado. Some of you might be able to tie that with the club's trip to the Fort McCavitt. Okie-Tex, we got Sun and Moon on October, all the way down. And discussions are still going on with Magnolia Creek and Bay Oaks Golf Course to get a couple of events out there. All right. Trip to the Messier Marathon. Fred and Sandra Miller represented JSCAS. We had these three people representing FBAC. I'm kind of, I didn't put that right, did I? Representing FBAC, that kind of all teamed up. They all helped out with the Star Party, which was good. The event was very well attended by JSCS, FBAC, San Antonio, and astronomy clubs. The skies were absolutely pristine, and everybody appeared to have a really good time. Upwards of 35 to 40 people were apparently there. I know there was concern from this club about getting everything meshed in, but it seemed like on the side of the parade grounds was where JSCAS was, and just a little bit further to the west was where most of the Messier Marathons were. So there was a little bit of distance separation. So this is just me talking hindsight. Maybe we should have kept our original date, because our April trip to the fort was a complete washout, as you likely know. All right, March 28th, Hack Winery event. A really big thanks to Chris, Stan, Jerry, Bai, Reed, Bob, and Leslie Eaton, and Connie and I were there. Estimated 150 to 200. You had camera lenses and all sorts of stuff. We got a stand there with a solar scope. It was a really good event for all. Chris showed off this cute little thing, which is nifty. I still want to try to look up more about it. Got Stan down here with one of his scopes that we now know, since he's got so many. Chris hiding behind his big boy. Connie holding court. People down here with all sorts of things going on. It was a really good and fun event. And then Reed was there with his C-Star. He and I kind of been, for the past few outreach events, kind of been playing a game off of each other. He'll cue the event, cue up the object in his C-Star. I'll cue it in the scope so they can see visual and the EAA version of it. Works out pretty well. All right. Sadly, the April trip to the fort was completely toast. It was killed by weather early on. I think, as you know, on the list,
It pretty much died by Tuesday night. But I ended up on a couple of phone calls with Kevin, who's really reiterating he's got the full support of THC, the Texas Historical Commission, and they definitely want us out there. But the only catch is we can only stay for free if we do the Star Party. That was the bitch and screaming about some of the people, particularly Fred. Fred was not particularly pleased at the Messier Marathon because when the marathon was over Saturday morning, 3/4 of them picked up and left. And as far as the fort and the THC is now concerned, that doesn't make them volunteers. That makes them visitors, in which case $25 a night. If we want to stay for free, you've got to do the Star Party. That's where that's where the kicker is. And I get it. And we've basically, that's been the unwritten rule that we have followed for, however many years have been going there. So I fully agree with it. Ford officially called it off Wednesday morning because he had to put out it on the website and call, make sure the people in Menard didn't make the 24-mile trip up to the fort. But the weather was absolutely dreadful. Okay, April 25th, Hack Winery. Very deep appreciation to Chris and Bob and Leslie. You guys three-way manned that. Was about 75 people there, 50, 75-ish? Somewhere in there. I have the asterisk next to your name because these are your pictures. So I thank you for them. A reasonable event, but I think it wasn't looking good. Saturday morning, I looked up, said, nope, this isn't happening. But the heavens managed to part for a little bit. It was one time where I think Astrospheric was actually right and opened up. And then I'm glad you guys had a really good event. We were a little occupied that Saturday and couldn't make it. Where'd it go? This is solar scope? Solar. Okay, I was wondering that because of the angle at which it was pointed. And binoculars. And again, thanks guys for manning that one. And okay, thank you. Thank you. I was concerned that somebody wouldn't get it. But if you've ever worked on a car, half your bolts are 10 millimeter, and that's a 10 millimeter socket is the one you're always looking for. I got to the point, I got a little magnetic thing with 10 millimeters of varying shapes and sizes, so I always got one, so I don't have to, where is the damn thing? And I saw this, I said, that's got to be my final slide. All right.
All right, thank you, David. Okay, so our meeting next month will be here again on June 12th, and we'll do another series of short presentations by JSC AS members. We had enough presentations. We felt like we could make 2 meetings out of it, and plus we didn't have a speaker for June, so that worked out just fine. And hope you guys can all come to that. Door prizes. Did everybody get a door prize ticket? Did you not get one? Oh, you got one. Okay. Anybody not get a door prize ticket? Okay, then.
Guess I probably should figure out what kind of door prize we got here. I think I got it figured out.
Okay. You guys ready? Look at your ticket. Okay. I know. I'm getting my glasses out. Sorry. Okay, first one. 1, 2, 6. Last 3 numbers, 1, 2, 6. All right, come on down here. The guy was talking on a cell phone. Get yourself down here. We got a moon map. Oh, I got a DVD set of, this is pretty cool, Stephen Hawking's Universe. That's pretty good. DVD set. I got a moon map. I got a DVD about comet collisions. Want to get in collision with a comet? I got a sticker for your car that says, let's sleep under the stars. So we get a choice. Yeah, which one you like? I'd go with that. You got it. Yeah, you can keep that. I trust you. What?
What did the sticker say?
I told him, I said, let's
Sleep under the stars.
Oh, let's sleep under the stars.
Yeah, you guys donated these stickers. Those are your stickers, Leslie. All right, here we go. 135. 135. 135. Oh, it's David. I know what David was. David wants a moon map because he's so excited about the moon. Okay, let's see, David. Oh, David, you know what? I don't know if you got one of these or not. I got one of these signs that says objects in the warning. Objects in the telescope are farther than they appear. I got one of those.
I have ones for my lasers at work that says, don't look in the laser with your one remaining eye.
That's good too. I got comet collisions. I've got, hold on, don't go away. Oh, I've got Exploring Amateur Astronomy, a book. Hold on, David, don't go away. I'm not done yet. Oh, I got one pair of astronomy socks with astronauts on it. Ooh, there you go. Woohoo! Got the socks. All right, David. Next one. Sorry, guys, that was the last pair of socks, but I'll get some more. All right, 140. Oh, Chris, come on down here, Chris. Woohoo, Chris. Let's see. What do you guys think Chris would like? I got a moon map. I got, you know what, Chris? Wait a minute. Somewhere in here. I got one of these things you can put your cell phone on your eyepiece.
I got 3 of them.
You got 3 of those. That was the shirt you're wearing. Here, Chris, I'll take my shirt off. Okay, I got Experiencing Hubble, Understanding the Great Images of the Universe. I got Black Holes Explained, which also comes with a book. I've got, hold on. Oh, you like that thing? Hold on. Yeah, you know, guys, listen, it's okay to tell me what you want. If you see it and you want, like this thing, I told you about that. All right. Good, there you go. Good. Good. Sometimes I forget what I'm talking about when I get up here. Okay, couple more. 145. 145. B, come on, B. Oh man, you know, last time B got a meter. I think. No, you got a book about electronics.
Yes.
I got Black Holes Explained with a book and a DVD. I got Comet Collision. I got Exploring Amateur Astronomy. Hold on. You like this one? Really? Okay, great. You know, she's an intellectual. You know, she always goes for the books because she's smart. Okay, this is the last one. I hope it's yours. 138. Who's 138? Oh, Lance, come on, Lance.
You know what we want.
Well, what do we want? I don't know. Did you see anything you liked? I got a moon map. I got Tours of the Night Sky. I think that's a DVD, I guess. Comet Collisions, Black Holes Explained. Lance, what do you guys think Lance would like?
What do you got?
I'm trying to think of what Lance would like. I've got a meter that worked the last time it was used.
Oh, no, I have about 10 of those.
Oh, wait a minute, Lance.
Oh, that's so cool. Well,
You don't want that.
no, I'll pass on that.
Okay, I've got Experiencing Hubble, Understanding the Greatest Images of the Universe.
Okay.
The great courses. This
Yeah.
is really good.
Yeah, we'll get that.
That's
Okay.
that's intellectual also.
And here's my
Oh,
ticket
you
to
can
prove
keep it.
it.
That's a souvenir.
Oh, gosh, thank you.
Yeah, that's all right.
A winning ticket.
Yeah. Okay, boys and girls. Thank you very much for coming. See you at Mod Pizza. Oh, boy. Missing something. Oh, there it is.